Okay, good morning students. In previous class we explained the definitions of inverse trigonometric functions and where they are defined, the range and domain of the functions, and then principal branch values of the functions. Today I am going to explain the properties of the inverse trigonometric functions. The first property is sin of sin inverse x is x. Sin of sin inverse x is x, which is valid for all x that lies between -1 and 1. That means x belongs to the closed interval -1, 1. Similarly, sin inverse of sin theta equal to theta, where theta lies in the closed interval -π/2 to π/2. Similarly, cos of cos inverse x is x in the rest, and cos inverse of cos theta equal to theta, and so on in their respective restricted domains. Now, sin of sin inverse x equal to x, it is valid for all x that belongs to the closed interval -1, 1. Why? Here sin inverse x is defined from closed interval -1, 1 to -π/2 to π/2. Hence, keeping the domain of this function in view, you have to take this condition. Now, coming to the proof of these properties, I will explain one property, proof of one property. In the functions, we know that suppose f is a to b, a bisective function, then it is invertible, its inverse exists, and it is defined from b to a. If f is a to b is a given function, its inverse, f inverse is defined from b to a. We know that f inverse circle f is the composite of mapping of these two functions. F inverse circle f is defined from a to a, which gives us the identity over a. Similarly, f circle f inverse is defined from b to b, the identity over b. Keeping this concept of the functions in our mind, let us take sin x is the function, suppose defined in its restricted domain -π/2 to π/2 to -1, 1. Once the sin x, the sin function, is defined over this interval, it is clearly bisective, hence its inverse exists. Sin inverse x is defined from -1, 1 to -π/2 to π/2. Now coming to, let us consider this is f, this interval as a and this interval as b, so that it becomes f inverse, it becomes b, it becomes a. Now apply this concept. F circle f inverse, f circle f inverse, f means sine of sin inverse x. Now sin of sin inverse x, sin of sin inverse x is x. Sin of sin inverse x is x, because sin of sin inverse gives us the identity mapping which maps x to x itself. Hence, sin of sin inverse x equal to x, where x lies within the domain of the function sin inverse, that is f inverse, which is nothing but for all x that belongs to -1, 1. Similarly, sin inverse of sin x, sin inverse of sin x, that is f inverse circle f, that is identity function defined over the domain A. The domain of sin inverse of sin theta, of course, here theta lies within the interval minus pi by 2 to pi by 2, the domain of the sine function itself. So, sin inverse of sin theta gives us the identity mapping over minus pi by 2 to pi by 2. The identity mapping maps theta to theta, where theta lies within the limits minus pi by 2 to pi by 2. So, all these properties are nothing but the immediate consequences of this concept, composition of mapping concept, f and f inverse composition. Taking one trigonometric function as f and its inverse function as f inverse, you can apply the same concept to the other properties, other trigonometric functions also, which gives us these different properties. Cos of cos inverse x equal to x. Here this is f inverse and this is f, and this is f and this is f inverse. Like that, you can develop the remaining all properties here. Now, so the first property is nothing but the immediate consequence of this result, f circle f inverse or f inverse f circle. Now the second property, coming to the second property. Sin inverse of minus x. Sin inverse of minus x is minus sin inverse x. Similarly, cos inverse of minus x is pi minus cos inverse x. Tan inverse of minus x is minus tan inverse x. Cot inverse of minus x is pi minus cot inverse x. And secant inverse of minus x is pi minus secant inverse x, whereas cosec inverse of minus x is minus cosec inverse x. Sin inverse of minus x is minus sin inverse x for all x that belongs to minus 1 comma 1. And cos inverse of minus x equal to pi minus cos inverse x is valid for all x that belongs to minus 1 comma 1 itself. Tan inverse of minus x is minus tan inverse x is valid for all x that belongs to or itself. Cot inverse of minus x equal to pi minus cot inverse x is valid for all x that belongs to or itself. Secant inverse of minus x equal to pi minus secant inverse x, and cosecant inverse of minus x is minus cosecant inverse x is valid for x belongs to minus infinity to minus 1 union 1 to infinity. Sin inverse of minus x is minus sin inverse x. Similarly, the other inverse trigonometric functions. All the properties of the inverse trigonometric functions are discussed in their respective domains, principal branch values of the trigonometric functions and their respective domains also. Now coming to proof of these properties, I will explain one proof. Sine inverse of minus x is, I will show sine inverse of minus x is minus sine inverse x. For that, let sine inverse of minus x equal to theta. Let sine inverse of minus x equal to theta, where x lies between minus 1 and 1, the given domain of x, and since sine inverse value lies between minus pi by 2 to pi by 2, I will take theta in its principal branch values as minus pi by 2 to pi by 2. So let sine inverse of minus x is theta, then theta lies between minus pi by 2 to pi by 2. So that implies sine theta becomes minus x. Once you apply sine on both sides, sine of sine inverse gives us minus x itself, and it becomes sine theta. Sine theta equal to minus x. That implies x takes the value minus sine theta, which implies x equal to sine of minus theta. Since by trigonometric results, sine of minus theta is minus sine theta, already we know it. X equal to sine of minus theta. Here minus sine theta. Once theta lies between minus pi by 2 to pi by 2, minus theta also lies in this same interval, minus pi by 2 to pi by 2 itself. Hence it is invertible. Hence you can write sine inverse x as minus theta. Sine inverse x as minus theta. Since minus pi by 2 is less than or equal to theta is less than or equal to pi by 2 implies minus theta also lies between minus pi by 2 to pi by 2 itself. Hence it is invertible. Therefore, sine inverse of x becomes minus theta. That gives us sine inverse of x equal to minus of theta. Theta is sine inverse of minus x, because theta is sine inverse of minus x. So sine inverse of x equal to minus sine inverse of minus x. Therefore, minus sine inverse of x equal to sine inverse of minus x, which is our required result. Sine inverse of minus x equal to minus sine inverse x. So this is the proof of sine inverse of minus x equal to minus sine inverse x. Similar arguments we can extend in case of tan inverse of minus x equal to minus tan inverse x, and cosecant inverse of minus x is also minus cosecant inverse x. You can extend the same arguments in their respective domains to the tan inverse of minus x and cosec inverse of minus x. Now I will explain cos inverse of minus x equal to pi minus cos inverse x. Now to prove this value, let us consider proof of the second one. Let cos inverse of minus x equal to theta. Let cos inverse of minus x equal to theta. For minus 1 is less than or equal, x is less than or equal to 1, and theta lies in the principal branch values, that is 0 to pi. Let cos inverse of minus x equal to theta, where theta lies between 0 and pi. I am taking the restricted domain of cos the value to get cos inverse here. In this domain it is clearly invertible, hence I am restricted the discussion to principal branch values only. So cos inverse of minus x equal to theta, that gives us cos theta equal to minus x. Cos theta equal to minus x, which is minus cos theta equal to x. But minus cos theta may be written as cos of pi minus theta, since cos of pi minus theta takes the value cos of 180 minus theta, which is minus cos theta. 180 minus theta falls in second quadrant. In second quadrant, cos is negative, hence we get minus cos theta. So, cos of pi minus theta equal to x. Now, cos inverse of x, apply inverse cos inverse on both sides. Cos inverse of x becomes pi minus theta. Cos inverse of cos pi minus theta, which gives us pi minus theta. Since here cos inverse can be applicable because pi minus theta always less than pi. Since theta lies between 0 and pi, implies minus theta lies between minus pi and 0. Adding pi throughout the inequality. Adding pi throughout the inequality, we get 0 is less than or equal to pi minus theta is less than or equal to 0 plus pi, that is pi. Since pi minus theta lies between 0 and pi, it is invertible, it becomes bisective, hence cos inverse exists. Once you apply cos inverse on both sides, cos inverse of x becomes pi minus theta. But theta is cos inverse of minus x. So, therefore, cos inverse x equal to pi minus of cos inverse of minus x. Therefore, interchanging these two, we get cos inverse of minus x equal to pi minus cos inverse of x, which is our required result. Cos inverse of minus x is pi minus cos inverse x, which is valid for all x that lies between minus 1 and 1. The similar arguments you can extend in case of secant inverse and cot inverse also in their respective domains, given domains. Coming to third property of inverse trigonometric functions. Sin inverse of 1 by x is cosec inverse of x, which is valid for all x that does not lies between minus 1 and 1. That means x belongs to minus infinity to minus 1, closed at minus 1, union 1 to infinity, closed at 1. That means x takes both the values 1 and minus 1. Similarly, cos inverse of 1 by x is secant inverse x, whenever x does not lies between minus 1 and 1. Tan inverse of 1 by x is cot inverse x in case of x positive, and in case of x negative, it takes cot inverse x minus pi. So, this is the third property of inverse trigonometric function. Now, I will give the proof of the first one. Coming to the proof of the first one, sin inverse of 1 by x is theta. Let sin inverse of 1 by x is theta. Taking theta as sin inverse of 1 by x, here theta always lies between minus pi by 2 to pi by 2. Just our discussion is confined to principal branch values of inverse functions. Hence, theta lies between minus pi by 2 to pi by 2. So, 1 by x equal to sin theta. Operating on sin on both sides, we get 1 by x equal to sin theta. Since 1 by x equal to sin theta, x becomes 1 by sin theta, which is nothing but cosec theta. As theta lies between minus pi by 2 to pi by 2, cosec is invertible. Hence, you can apply cosec inverse on both sides here, so that we get cosec inverse x becomes theta. since theta lies between minus pi by 2 to pi by 2 and cosec inverse is applicable here. Cosecant is the function cosec inverse exists in case of theta lies between minus pi by 2 to pi by 2. So, that is cosec inverse x equal to sin inverse of 1 by x, because theta is sin inverse 1 by x. Hence, sin inverse of 1 by x is cosec inverse x. This is the first property here. Similarly, you can apply the same theory to prove cos inverse of 1 by x is secant inverse x, where x does not lies between minus 1 and 1. The similar arguments you can extend in case of dealing the proof of this one. Cos inverse of 1 by x is secant inverse x. So, I will give the proof of the third one. Tan inverse of 1 by x is cot inverse x whenever x is positive. Whenever x is negative, cot inverse x minus pi. So, let us consider cot inverse x is theta. Let us consider cot inverse x is theta for x positive. The first case is this. X being positive, let cot inverse x is theta. Since x is positive, cot theta is positive. Cot theta is positive, then theta lies between 0 to pi by 2. Cot theta is positive in first quadrant, hence I am taking our arguments is confined to the first quadrants. Theta lies between 0 and pi by 2. From this, cot inverse of x equal to theta implies cot theta becomes x. So, cot theta may be written as 1 by tan theta. So, 1 by tan theta equal to x, hence tan theta equal to 1 by x. So, here theta lies in 0 to pi by 2, it is invertible, hence tan inverse can be applied here. So, that once you apply tan inverse on both sides, we get theta equal to tan inverse of 1 by x, since theta lies between 0 and pi by 2. Therefore, what is theta here? The theta is cot inverse x, hence cot inverse x becomes tan inverse of 1 by x, the first case. Coming to the second case, whenever x is negative. When x is negative, then theta lies between pi by 2 to pi. Since cot is negative in the second quadrant, here I am taking the angle in the second quadrant. Cot inverse x lies in the 0 to pi. Hence, our discussion is confined to first and second quadrants only. Once x is positive, I am taking in the first quadrant, and once x is negative, I am taking the second quadrant angle. So, our discussion is restricted to this interval 0 to pi, first and second quadrants. So, once x is negative, then theta becomes theta lies between pi by 2 and pi. Once theta lies between pi by 2 pi, minus theta lies between minus pi and minus pi by 2. So, that adding subtraction of theta, subtraction of pi from this inequality, we get minus pi by 2 is less than theta minus pi is less than 0. Just I am subtracting pi in this interval, pi by 2 minus pi. Pi by 2 minus pi gives us minus pi by 2. Theta minus pi is less than pi minus pi 0. So, immediately theta minus pi lies between minus pi by 2 to 0. Now, taking cot inverse x as theta as usual, x becomes cot theta, 1 by x becomes tan theta. This tan theta now may be written as minus tan of pi minus theta, minus tan of pi minus theta, which is tan of theta minus pi, pi. So, 1 by x becomes tan of theta minus pi. Here theta minus pi lies between minus pi by 2 to 0. Since tan inverse function lies within minus pi by 2 to pi by 2. Here theta minus pi lies between minus pi by 2 to 0. The sub interval of this interval minus pi by 2 to pi by 2. Here inverse tan exists, hence you can apply tan inverse on both sides, so that we get tan inverse of 1 by x equal to theta minus pi, where theta minus pi lies within the interval minus pi by 2 to 0, the restricted domain. To make this invertible, this tan invertible, you have to prove theta minus pi lies between minus pi by 2 to 0. So this is the proof of tan inverse of 1 by x equal to cot inverse x minus pi for x less than 0. For x being positive, tan inverse of 1 by x is cot inverse x. X being negative, then tan inverse of 1 by x becomes cot inverse x minus pi. This is the property 3. Coming to fourth property of inverse trigonometric functions. This is very important property. Very important property in inverse trigonometric functions. Sin inverse x plus cos inverse x is always pi by 2. It is always constant, pi by 2. This relation is valid for all x that lies between minus 1 and 1. X belongs to the closed interval minus 1 comma 1 only, it is valid. Sin inverse x plus cos inverse x is always equal to pi by 2 whenever x lies between minus 1 and 1. Similarly, secant inverse x plus cosec inverse x is pi by 2 whenever x does not lies between minus 1 and 1. That means x lies within the interval minus infinity to closure at minus 1, union closure at 1 to infinity. The common domain of secant inverse and cosec inverse x, you can observe it. Similarly, the third one is tan inverse x plus cot inverse x is pi by 2 for all x that belongs to R. Now, these three are very important relations in inverse trigonometric functions, and even in dealing the problems they play vital role. So, coming to the proof of the first one. Let sin inverse x equal to theta. I am taking this inverse function as theta. You may take cos inverse x as theta, and you can extend the same arguments in such case also. Let us consider sin inverse x equal to theta whenever x lies between minus 1 and 1. This is given. In such case, sin inverse x always lies between minus pi by 2 to pi by 2. So, theta lies between minus pi by 2 to pi by 2, because our arguments are confined to principal branch values. So, sin inverse x is theta implies x becomes sin theta. Applying sin on both sides, we get x becomes sin theta. That implies x equal to, this sin theta may be written as cos of 90 minus theta. That means pi by 2 minus theta, because cos of 90 minus theta gives us sin theta. So, sin theta may be expressed as cos of 90 minus theta here. Here we have to get cos, a relation between sin and cos, Hence, I am writing sin in terms of cos as sin theta equal to cos of pi by 2 minus theta, which gives us cos inverse x equal to pi by 2 minus theta. To write this, it is invertible. That means pi by 2 minus theta lies between 0 and pi. Just I am showing that here. Once theta lies between minus pi by 2 to pi by 2, minus theta also lies between minus pi by 2 to pi by 2. Okay. Adding pi by 2 throughout the inequality, clearly minus pi by 2 plus pi by 2 gives us 0, pi by 2 minus theta, here we get, is less than or equal to pi by 2 plus pi by 2 gives us pi. Hence, this value lies within the restricted domain of cos, which is invertible in that domain. So cos inverse exists for this value pi by 2 once x equal to cos of pi by 2 minus theta. Here cos inverse exists. Hence, cos inverse is applicable on both sides. because pi by 2 minus theta lies between 0 and pi. So cos inverse x becomes pi by 2 minus theta. So cos inverse x equal to pi by 2 minus what is theta here? Theta is sin inverse x. Hence you can replace theta with its original value sin inverse x. Now transfer this term sin inverse x to this side. We get the required result sin inverse x plus cos inverse x equal to pi by 2. Sin inverse x plus cos inverse x equal to pi by 2, which is valid for all values of x that lies between minus 1 and 1. This is the first case. The same arguments you can extend in case of tan inverse x plus cot inverse x equal to pi by 2 to show tan inverse x plus cot inverse x equal to pi by 2 for all x that belongs to R. The same arguments over there given domains and restricted principal branch values, the same arguments you can extend and you can prove tan inverse x plus cot inverse x equal to pi by 2. That is easy. That is left to you. Now coming to the second one, secant inverse x plus cot inverse x equal to pi by 2 whenever x does not lies between minus 1 and 1. Coming to the proof of this relation, let secant inverse x equal to theta. I am taking secant inverse x as theta. Here x does not lies between minus 1 and 1 and secant inverse x lies in 0 to pi. So theta lies between 0 to pi, where theta not equal to pi by 2. Since secant inverse x defined in such a way, based on the domain and range of the inverse function, it is clear that theta lies between 0 and pi, where theta not equal to pi by 2. So that from secant inverse x equal to theta, it implies secant theta becomes x. Secant theta may be written in terms of cosec as cosec inverse of pi by 2 minus theta. Cosec inverse of pi by 2 minus theta. Cosec 90 minus theta gives us secant theta. Cosec 90 minus theta gives us secant theta. Hence secant theta may be expressed as cosec of pi by 2 minus theta equal to x. So apply cosec inverse on both sides. You get cosec inverse x equal to pi by 2 minus theta. It is applicable whenever pi by 2 minus theta lies within the interval minus pi by 2 to pi by 2, where pi by 2 minus theta not equal to 0 only. Because cosec inverse x defined in such a way between minus pi by 2 to pi by 2 and pi by 2 minus theta not equal to 0. So it is obtained since theta lies between 0 and pi and theta not equal to pi by 2. Minus theta also lies between minus pi and 0. So adding pi by 2 throughout the inequality here, we get minus pi plus pi by 2. Minus pi plus pi by 2 gives us minus pi by 2 is less than or equal to pi by 2 minus theta is less than or equal to 0 plus pi by 2 pi by 2. Whereas theta in such case becomes pi by 2 minus theta not equal to 0 since theta not equal to pi by 2. So here cosec inverse exists, hence you can apply cosec inverse on both sides. In such case cosec inverse x becomes pi by 2 minus theta, where theta is secant inverse x. So cosec inverse x equal to pi by 2 minus secant inverse x. Transfer this term secant inverse x to this side. Secant inverse plus cosec inverse x equal to pi by 2, which is our required result.